everyone. Welcome to today's Tuesday seminar series. Today we have Jamie Heather, who is the CEO of ZOZO. He's going to talk a little bit about his career and his pathway so far, and about algorithms. So without further ado, Jamie.
Thank you very much. So I should clarify, I'm the CEO of ZOZO New Zealand that has 11 people in it, not ZOZO Japan that has hundreds or thousands of people in it. So they're slightly different scale operations. But thank you all for coming. I'm going to run through, I've got about 40 or so slides, so I might need to burn through some of them. But my goal was to try and give some perspectives about my career as an algorithm developer so far. And hopefully you'll find them interesting to talk a bit about what it is I do as an algorithm developer, and then finish up with a little what we look for in algorithm developers when we're recruiting. So as you may know, algorithm, the word, was named after this chap who was alive about 1200 years ago. I'm not going to try and pronounce his name. If anyone's feeling brave, I'd be curious to hear how it sounds.
I can help you.
Oh, go ahead, yeah.
That's Khwarazmi.
Khwarazmi.
Al-Khwarazmi.
Al-Khwarazmi. It doesn't sound much like algorithm.
It's Al-Khwarazmi, algorithm.
Ah, okay. Persian, I think?
Yes.
Yeah. Okay, a Persian author. So more recently, Isaac Newton laid a lot of the groundwork, of course, for numerical methods and iterative methods. Amazingly, well before computers were here. So it kind of blows my mind, really, that Newton was able to think of all these advanced numerical methods without having any convenient device, even a mechanical device, to do any calculation on. But I guess this slide is just meant to say that algorithm developers have been around for a long time. It's not really a new career. But of course, algorithms are becoming much better known among the popular media. Almost every day now, there's a mention of algorithms in the news, quite often in some kind of bad or sinister context. The algorithms are either making fake news, or the algorithms are trying to replace humans, and so on. But there are lots of good applications of algorithms as well that maybe don't make the headlines quite so often. Good or bad, what is certain is that algorithms are now playing a huge part in our society, and they're going to define the future of mankind, I think it's reasonable to say without exaggerating. And of course, it won't just be the algorithms themselves, it will be the people that develop those algorithms that make that happen. So as I said in this talk, I'm just going to talk about my own personal experience as an algorithm developer, try and give some interesting technical insight into some of the things that I've done in my career, and the types of techniques I've used over and over and over again throughout my 17 years so far in algorithm development. And a bit of talk at the end about algorithm development as a career, as opposed to other related disciplines like software development or data science. So I was born in the UK, in a place called Southampton, which is a port famous as the port where the Titanic sailed from in 1912. I grew up in the 80s, which were an interesting era. I feel like there's quite a few people in the room here that remember the 80s. If you are not familiar with it, then it was a great era. We had computers. They're a lot slower, bigger and clunkier than computers today, but they could do computer graphics like this, amazing rendering here. So we had amazing computer graphics, and we had something called a synthesizer that could make amazing music to go with the amazing computer graphics. I don't know if any of you have seen the TV series Stranger Things. This is set in the 80s in America. And there's this great scene where Bob hacks into the lab security system, which I'm going to show here.
Bob, can you hear us? Loud and clear. Can you hear me back? Yeah, we hear you all right.
This is Bob. This is Bob coding. He's very quick at typing. He's in.
Good type. Open sesame.
Okay, Bob did it. So this reminded me of my childhood. One day, my father brought home a computer, a PC from work that looked a lot like that one. It had a text-only display, and you could use it for basic programming. And here's Bob's program. So it's 14 lines of code, 4 nested for loops. The operating system apparently supplies functions, built-in functions called get 4 digits and check password match, which was super handy because it would have taken Bob a lot longer otherwise. But this actually reminded me of the first program I ever saw, which was just a few lines of basic code. My dad wrote it, and it produced the multiplication tables, the 12 times tables. And it blew my mind that a few lines of code could do that. It could do what I'd spent the last 5 or 6 years of my life trying to learn. And for the computer, it was incredibly simple and easy. And from that point on, I spent quite a lot of my childhood, too much probably, coding and playing with code, trying to write programs, games, apps, generally on better PCs than this one. But it was a start for me of a coding career, and I realized that I love doing this. I love coding. And I hope that eventually I'd somehow find a way of coding as part of my job. So that was the 80s in Southampton. After that, I went to Oxford University. Of course, Oxford is this amazingly beautiful and old city. I was very fortunate to go there and gain a master's degree in mathematics, which is awesome. I love maths as well, so I found 2 things that I loved, coding and mathematics. But I had no idea what to do next. The general consensus is that mathematicians should either be accountants or school teachers. Neither of them really applied, but I didn't know what I wanted to do, and fortunately somebody solved the problem for me. A former contact gave me a job offer, and I went to work for a company in Guildford, which is a small town near London, and I started there as a technical consultant. This business was called Waterfall Solutions, and they're a very small startup company. I think I joined as the 3rd employee, and we worked in all these cool sounding areas. Most of our customers were military, UK defence. We did a bit of commercial stuff as well, but mostly defence contracting, working with vision systems and image processing algorithms. And I got to work in all these interesting areas on the right here. And after a while, I started to feel like my title of technical consultant was a bit vague, and maybe that what I really was an algorithm developer. Algorithms didn't get talked about as much back then. We did loads of cool stuff in our little team. This is just an example. This here, sorry about the jittering, I'm not sure why I'm doing that, but this is a panoramic imaging system mounted to the mast of a yacht. And we've registered all the images together, stitched them into one panoramic image. And the idea is that in the cockpit, the pilot could use that to keep an eye on what's happening around the vessel in real time as it sailed. We took that a step further and put image stabilization into that system. So now you can see the horizon is roughly level as the boat bounces around. So that was a kind of real-time registration system, or mosaicing system. Let's keep going. Okay, so that was my time in the UK. After that, I decided, after 5 years in the workforce, that it was time to have a break. I went on a mini sabbatical to Canada. I lived in the Canadian Rockies, which I think is the most beautiful place on earth. If you ever get the chance to go, I'd recommend it. And unfortunately, I did end up working as an accountant or a bookkeeper in an accounting firm for my 1.5 years there. There weren't too many professional jobs available in this tiny mountain town. Jasper has a permanent population of 5,000 people. So after my North American experience, I moved to Brisbane, home of the crocodile hunter at the time, in Australia. And I continued to work remotely for the UK company that I'd worked at before. And then from there, I finally made the leap to the world's best city, Auckland. And over the next 4 years, I worked in a number of different roles, and there's some slides after this to talk about some of those positions. But NextWindow, and then Compac, and then I started my own company, and that was bought in April this year, 2019, sold to a big Japanese company called ZOZO. And now I'm the CEO of ZOZO New Zealand. So going back, so the first company I worked at in New Zealand was NextWindow. They made optical touchscreens. This is just a kind of simulation or rendering. But the way these systems worked is they had tiny cameras mounted around the screen, and they looked out across the screen, and by triangulating what the various cameras could see, you could identify the position of a touch on the screen. For a single object, it was relatively straightforward, with multiple fingers on the screen at the same time. We had a lot of challenges with occlusions, and it was quite a lot harder to resolve what was happening. But I worked as a senior algorithm developer there, and worked mainly on multi-target tracking systems and a camera calibration algorithm. While I was there, I replaced the original calibration method, which involved a big, heavy jig with lots of pins, very expensive and difficult to make. We replaced that process with a milk bottle top. And we found that you could just move a bottle top around on the screen in any pattern you liked, and by running effectively just a modern calibration algorithm, we were able to recover the camera geometry without needing to have that very expensive mechanical jig. From there it was on to Compac. I was a vision research team leader there. Many of you are probably familiar with Compac already. So they make fruit sorting equipment. It's a pretty cool system. They sell this vision cabinet full of cameras, infrared and visible band cameras that image fruit as they pass through at a rate of 10 a second on each lane pass through the system. And they take images of it from multiple angles as it rolls through, and then try to classify the fruit into multiple different categories. From the best fruit would always go overseas and get sold for a premium, and the worst fruit would get sold in our supermarkets here. So that was quite an interesting job. Again, I mainly worked on camera calibration, 3D reconstruction algorithms, and we introduced machine learning techniques into that classification process. In 2014, with a couple of former colleagues, I started a company called Algorithm Team. Amazingly, algorithmteam.com was available. So we took that name and we decided to provide consultancy services to companies and industry around the world. And we picked up lots of clients in various different countries, eventually leading us to meeting ZOZO, or Start Today as they were called at the time. ZOZO is a Japanese company, and their CEO at the time, a chap called Mr. Maezawa, who made the headlines for buying the ticket from Elon Musk to the moon. In fact, he didn't buy the ticket, he bought the shuttle. So he's a Japanese billionaire, and he owns a company called ZOZO, and they sell clothes. They're an online fashion retailer. And they've been very successful at that. They're very well known in Japan. Outside of Japan, not so well known, but very well known there. And Mr. Maezawa had an ambition to be able to sell clothes online to people, but provide the confidence that it would fit when their package arrived in the mail. The way we did that was by developing what was called the ZOZOSUIT, which you can see here. This is effectively it's a stretchy elastic suit covered in QR codes. Every QR code is unique. They're non-stretchy, so however big or small the person is, we always know the size of the QR codes. And we were able to develop a system that just uses a smartphone placed on a table or a desk, looking at the person wearing their ZOZO suit, and they turn themselves around through 12 positions in front of the camera, and then we're able to reconstruct a fairly accurate 3D model of the body. And the idea was that this would be used to drive online sale of clothes, but especially a private brand of clothes. Clothes that were meant to fit you in a bespoke way, that were tailored to your body. It was a very ambitious project, and there were a few challenges. Ultimately, it wasn't quite as successful as Mr. Mizell had originally hoped. But we made the cover of Time magazine. This is our ZOZOSUIT just here. It's one of the 50 best inventions of 2018. And nearly 2 million people wore our ZOZOSUIT, mostly in Japan. But we have a data set of 2 million human bodies, which is probably one of the biggest data sets of its kind, if not the biggest in the world, I would guess. And by using that data set, we're able to do some data mining and train some effectively big data algorithms on that data set. And we now have a system that we can use to sell clothes to people in Japan just by being given a few basic parameters about their body. We can use those to correlate those effectively to the optimal size clothes for them to wear. It's not quite as accurate as putting on a ZOZOSUIT, but it's a lot easier. And that was kind of the happy ending to the ZOZOSUIT experience for Japan. It started this odd social phenomenon of people wearing ZOZOSUITs in public. In Japan, if you Google ZOZOSUIT on Twitter or Instagram, you'll just find thousands and thousands and thousands of really strange pictures. As I said, we were acquired by ZOZO earlier this year, and now we're continuing to develop new body and apparel-related technologies for ZOZO Japan. Okay, that's the preamble. I'm going to try and talk about some technical examples about what it is that I find myself doing most often as an algorithm developer. A few years into my career, I started to see a pattern in the type of work I was doing over and over and over again. And I started to form this opinion that almost everything is an optimization problem of some form. If there's a way that you can attach a number to the outcome of anything, where high is good and low is bad, or vice versa, if you can attach a number to it, then you can try and optimize that number to find a good solution. So in this case, this is something I stole from the internet, but this is meant to depict a situation where there's two variables, theta1 and theta0, two independent variables, and some function that varies as a function of those variables, j. And this is depicting a gradient descent algorithm where you start from some initial guess, and then you take a bunch of downhill steps, and eventually end up at a local minima. And which one you end up, which minima you end up at depends a little bit on where you start with steepest descent. So I'm going to drink some water. Now, having said that everything's an optimization problem, optimization itself is a really huge field. Some of the defining things are, is your problem continuous or discrete? Does it have constraints or bounds, or is it unconstrained? And even the nature of the objective function. So most of these methods I haven't really used a lot in my career, but this one here, least squares and analytical solutions have come up again and again and again. So I'm going to try and talk through some examples, give some examples of that for popular applications. I'm really not sure with these slides that are coming up whether everyone in here will have already done this and it'll be very boring and tedious and you'll feel like you're back at first year undergrad, or whether this will be actually a bit of a workout for your brain. There's quite a lot of maths coming in the next few slides, but I promise it will be over in 20 minutes or so. So the types of solutions that I've come across most often are exact solutions. Certain systems have analytical solutions, or they can be posed as a linear least squares problem, which again means they have an analytical solution. Those kinds of problems, if you can formulate your problem that way, then that's fantastic because you can get the best possible answer with very little calculation. Other problems though, maybe even the generality of problems don't have those nice analytical solutions, and then you need to use a numerical method, an iterative method, to find a solution, and hope you don't fall into a local minimum. So the next few slides I'm going to try and give some examples of those different types of problem. So this is about the very most simple fitting problem you can have. We've got some points in the xy plane, 4 points in this example, and we want to fit the curve through them. So I'm going to assume it's a polynomial curve. Of course, there's lots of other types of curve we could use, splines and so on. But here I'm using this polynomial model. And the goal of this process is to find a set of coefficients for this polynomial that will pass through these points exactly. So I guess in the simplest case, this polynomial could just be linear, just be a straight line, and I'd be fitting a line of, well, probably not a line of best fit because I've got 4 points, but in that case, the coefficients would be the gradient and the intercept if it was a line of best fit. More generally, I've assumed here that it's an nth order polynomial. So each one of these points xy is a sample. So there's x1, y1, x2, y2, x3, y3, and x4, y4. And each one of these, when I plug these points into here, I effectively have a system of linear equations. So the x's and the y's are known. So I'm going to plug my x's in here, and for any given guess for these unknown parameters, I'm hoping that my y's will come out the same as the observations. So this can be posed as a linear system. We put all these x's and all the powers of these x's into a matrix A, put all the y's into a vector B, and then the aim is to find the vector x, the parameter vector with these unknowns, such that AX equals B. That's just representing this model here in matrix form. And the naive solution to that is just to invert the matrix A, which works as long as that matrix A is square and non-degenerate. So in this case, I've got 4 points, which means a cubic is the curve that will fit exactly through those 4 points. Of course, this type of fitting problem doesn't occur very often in practice. It's much more common to have a lot of noisy data. Noise is everywhere, noise is in everything. And so rather than compute exact fits, what we generally want to do is try and fit, in this case, a curve of best fit or a line of best fit through these noisy points. So again, we have to choose how do we want to model this curve, and again, I've assumed a polynomial form, which means it's still linear in the unknown coefficients in those p's. Looking for a vector x that gives approximately the approximate solution. So when I plug in my point x using these coefficients, I want to get approximately the y values. What do we mean by approximately? Well, we have to somehow characterize that to be able to solve this problem. So if we let this f represent the difference between my prediction for the y value and the actual y observation, that's the residual, or the residual error. Then we want to try and, or the way I'm formulating this is to try and minimize the sum of these squared terms. So this is a least squares formulation. And it's linear because these individual f terms are still linear in the unknowns. So although there's a power of j up there that looks a bit scary, It's okay because we're trying to solve for the p's. We've got x and y values from here, and we're just trying to find a set of parameters p, and that equation is linear in those unknown coefficients. So we want to find a vector x that gives ax is approximately equal to b in a least square sense. And there's a few different ways of solving that. One common method is to use the so-called normal equations. And this is a very standard solution. If you have a problem like that, a least squares problem, then the textbooks will tell you this is the solution. You take your matrix A, which has all those x terms as before, transpose it and multiply that with itself, and that gives you a square matrix, which means you can then just go ahead and invert it to recover the solution. In practice, you don't actually have to invert the matrix. There are more efficient numerical methods for doing that, such as LU decomposition. So most programming languages have routines that you can tell it you want to solve a problem AX equals B, and they'll figure out the answer without explicitly inverting anything. Okay, so this is the line of best fit through those points. That's choosing a value of 1 for n. That's the quadratic fit, cubic, and I'll start jumping a few. This is the 5th order polynomial, and that's a 9th order polynomial. Any opinions in the room about what we should be going for here? I'm tempted to take a vote, but maybe that's unnecessary. Yeah, which one's the best fit? Tricky question. In
Cubic, maybe?
Cubic? A vote for cubic? Yeah, looks quite nice. Any other offers? The best fit for this data?
Depends whether the scatter is noise or actual data.
Good point. Yeah, and I haven't given you enough information to deduce the answer to that. But yes, that's fairly critical. I guess one of the giveaways is there's a few cases here we've got points that are very close in X but have quite a big difference in Y, which suggests that this could be quite noisy data. Of course, you can't really tell the answer, but it's actually a quadratic. The underlying function is quadratic, and I just threw in some random noise. Humans love to see patterns in the data, and naively, lots of people will choose this one. But you can already see here that we're getting some pretty erratic behavior of this underlying function, which is unlikely to be part of the data unless we know that the data has very low noise. And if we go a step further to a 13th order polynomial, then we get this crazy overfitting. I really like these sorts of examples because they illustrate the problem very clearly. In machine learning, people almost invariably seem to tend towards overfitting their data. They come up with a model, they compute their coefficients, and it looks great, it's giving great results, and then you bring in some new data, and suddenly the results don't seem so great anymore. Of course, there are many methods for dealing with that, such as cross-validation. But yes, we as humans, we like to see patterns in data that aren't really there. Okay, so these are very simple examples of exact solutions and least squares. They can be built out and extended. So we can say, well, what about if we have a function of 2 variables? So a function, I've got a whole bunch of points here in 3D, x, y, z Cartesian space. And can we find a surface, z equals some function of x and y, that fits that data? So the answer is yes, of course. We can use a very similar approach to the one I defined just now. This is another polynomial expression. We're just going to take a combination of x and y's to various powers. So in a simple case, we could say, let's try a quadratic fit. So for n equals 2, I'm going to assume that this function has a form like this. A constant term plus an x and a y term, and x squared, xy, and y squared. Again, despite those squares, it's linear in the unknowns. So when we talk about linear or non-linear, we're referring to the unknowns. So again, we want to find a solution vector x that solves this equation. Ax is approximately b. I've only got 6 unknowns here, 6 degrees of freedom, and 100 points over there. So this is very much an underdetermined system. So I need a least square solution, and I can get that by solving this equation here. Normal equations again. And that's what that fit looks like. Another variation on this is to say, well, what about if we have lots of independent variables? So suppose we've got various measurements. For instance, it could be data about a person, their height, weight, waist size. I'm abusing notation a little bit here. This was previously x and y. Now it's x1, x2, x3, up to xn. So I've got n different measurable parameters. And suppose I'm trying to predict the best fitting gene size for each person. So one option here is just to assume a simple linear relationship, just that this output y is related to the inputs through some linear combination. Suppose we have a bunch of examples or samples. Then again, we can form a solution matrix and a solution vector, bundle all our unknowns into a vector x, solve the least square systems. Solve the least square system. But the problem with this is if we have a lot of input parameters, then a lot of unknowns, a lot of unknown coefficients, then we can easily overfit the data, which is the problem we saw with the curve fitting example just a minute ago. So this is an example of overfitting. So if I just go ahead, I think in this simulation here, I simulated about 12 observations, and I had 10 independent variables. And then I solved this least square system and came up with this solution. It's a lot harder to visualize what's going on here because we're now in a multi-dimensional space. I just said there were 10 unknowns, n is 10. And we can't really plot out or visualize a 10-dimensional space very easily. All we can really do is plot slices of that 10-dimensional space. We can pick any 2 of those independent variables and we can plot those against y, but it's quite difficult to get a good visualization. So what I've done here instead is I've used leave one out cross-validation. And these are the true values plotted against the predicted value. So in an ideal case, if my regressor was working perfectly, then all these points would lie on that line, y equals x. And they don't though, there's quite a lot of scatter, and that's because we've overfitted the data. So I just introduced the term leave one out cross-validation. What that means is we take out one of these samples, we train the algorithm or run this least squares fit for the remaining samples, and use that to predict the outcome for the left out sample. This is a common method used in machine learning, and the idea is that you're making a semi-independent estimate for each one of these samples. So the solution for that problem is to introduce a regularization term, or at least one of the solutions. So instead of just minimizing this objective function made up of the differences between our predictions and our targets, we introduce this extra term, and here we're penalizing large values of these coefficients. So we prefer the coefficients to be small. We could, if we had default values for these coefficients, we could minimize the difference from the default values there instead. So there's a few different ways of posing this. So this lambda is a constant, and you can set that to whatever you like. If you make it really big, then this term starts to dominate. Conversely, if you make it very small or 0, then this turns back into the regular least squares solution I talked about before. So if you hear people talk about tuning the regularization parameter, they're just trying to find values for that give good results via cross-validation. This particular choice of regularization term is called L2 regularization because it's a sum of squares. You can have L1 regularization as well, where it's a sum of mean absolute values, or the Frobenius norm. There's various different ways to apply that regularization. The nice thing about L2 is we still have an analytical solution. This is still just a sum of squares of linear terms. So informally, we're looking for AX equals B, or approximately B, and X is approximately 0. That's kind of what that's doing. And the way we can obtain that is by bundling these, or augmenting our solution matrix with these extra terms, and then solve that augmented system. None of this is really very new. It's all in textbooks, and I've got a reference to a textbook later on. But for me, learning about this and understanding this and how this works and how to apply it to different problems has been really very valuable in my career. And I'll talk a bit more about applications of that later. Okay, so in case you missed it, that's the unconstrained system. And after introducing a regularization term, the leave one out cross-validation did give better results. We're getting closer to that line, y equals x. This is known as ridge regression, which is one of the most popular machine learning regression techniques, linear regression methods. Scikit-learn has some fantastic documentation around regression. I recommend reading it. It's a good way to get the crash course in using machine learning for regression problems. Their terminology is different. They use W where I used X, and they use X where I used A. So apologies for that. Alpha instead of lambda. They got their terminology all wrong. But this is actually the standard terminology that almost everybody uses in machine learning. That's a ridge regressor. If you put an L1 norm on the end there instead, that has some better properties mathematically. It's less susceptible to outliers, for instance. You get this slightly different objective function. And from a solution perspective, that makes it a lot harder to solve. Because with that sum of absolute values, that's neither a least squares type problem, and it's not linear. That modulus function has a big corner at the origin at 0. So you have to use iterative solution methods in that case. So that one's called lasso, a very famous type of regressor. There's another famous standard regressor, linear regressor, called elastic net. And that has both an L1 norm and a L2 norm appearing in it, which is claimed to give better results under certain applications. In practice, if you're using scikit-learn and you're switching between these, what you'll find is with the ridge and the least squares, they're very predictable and stable. If you don't have to initialize them with a guess, you just solve the matrix equations and you get the answer, the solution. The only solution, at least if the problem is well defined. Whereas with these methods, you start them off a certain guess, and they iterate, and iterations are generally quite slow, and then they may or may not get to a good solution. So a bit more care is needed to get this working properly. And in general, if you have a linear regression problem, then I strongly recommend you consider starting with one of these methods as an analytic solution. Okay, what about nonlinear problems? Many objective functions that we're interested in formulating just don't fit that, prescription of being a sum of squared values of linear functions. There's a few different possible options in that case. I'm going to be careful I don't run out of time here. One of them is to try and reformulate your problem so it becomes linear. Another one is to locally linearize your solution. So you make a first order approximation and solve for that as if it's a linear system, and then take that new answer and iterate. Failing that, if you can still formulate it as a least squares problem, but with the f terms being non-linear, then you can apply the Levenberg Marquardt algorithm, which I love. It's a fantastic general purpose algorithm. It's got great convergence properties, and I'll talk a bit more about that in a moment if I have time. And failing all of that, if your objective function just doesn't fall into any of those categories, then you can try a general iterative method, such as gradient descent or a quasi-Newton method. So very briefly, this is a kind of contrived example, but if you're looking for a 2D mapping from a set of points x, y to a new set of points u, v, one type of mapping you could try is a similarity transform. So that represents a combination of translation, rotation, and scaling. It doesn't allow for affine or perspective type distortions, but it's a simple transform. And if you parameterize your problem with theta, the angle of rotation, s is the scale, then tx, ty are the translation in the x and y directions, then you might come up with a form for the mapping that looks like this. So these are the equation, the coordinates u, and the coordinates, u and v related to x and y by this 2D rotation and scaling and translation. Now this is non-linear in the unknowns, because we've got trig terms appearing in here and products, a theta term there multiplied with an s term. So this is a non-linear problem in the unknowns. But for this case, there's a handy trick you can do. You make a substitution and replace the product of these two s and theta terms with an a and b, s cos theta, b sine theta, and then you can rewrite the problem in a linear way. So there's still 4 unknowns, but now it's unknowns a, b, tx, and ty. That's a nice linear system. And you can just go ahead and solve that using a linear method, an analytical method. And then if you want to get back your scale and theta, then you can extract those back from A and B at the end. This is a slightly more relevant example, probably. Projective transforms are used to represent mappings between different camera views. So in this case, there's a checkerboard that's seen in 2 different views. And if you assume that there's no lens distortion present, then this type of mapping will relate the coordinates in one image to the coordinates in another image. And if you have a set of point-to-point correspondences, so here I've got four points in one image and 4 points in the other image, then you can go ahead and try and solve that to compute that projective mapping. But again, you run into a problem very quickly that this is non-linear in the unknowns. So here the unknowns are these coefficients, A1 through to A8. And because some of those coefficients appear in the denominator, we can't use the linear method or the analytical solution. But if you multiply the denominators up to the top and then do some rearranging, you end up with these 2 equations which are linear. So we've got these xu, yu terms here, but that's okay. Those x's and y's are 6 numbers that come from our tie point correspondences. And these equations are linear in these unknown coefficients. So again, we can now go ahead and solve for those. There's just a small caveat that because we reformulated that, the thing that we're minimizing now is not Euclidean error in the image. We're minimizing something else, something relating to these algebraic equations. So this is called an algebraic solution, and it gives us an answer that's generally pretty good, but not optimal in a geometric sense. So people often apply, People often apply the algebraic solution as a way to initialize an iterative geometric refinement. Anyone here who has worked with homographies before and cameras will be wondering why I'm working in inhomogeneous coordinates as opposed to homogeneous coordinates, but it's just easier to understand it for this example. Okay, linearisation. This is another quite contrived example, but it's about the simplest I could come up with. So let's suppose we have two sets of points, 2 point clouds, and we know the correspondences between all these points. This is a scan of a foot model here. And we want to try and find a rotation R that will bring those 2 feet into alignment with each other. Oops. Okay, now one way of representing rotation matrix is using Euler matrices. It's not one of the most elegant forms, but again, easy to understand, intuitive to understand. So there's 3 degrees of freedom in a 3-dimensional rotation, but this thing is horribly non-linear. I wouldn't want to try and differentiate through that. But what we can do is say, well, let's assume we have an initial guess R0 for this rotation. And in the worst case, that could just be the identity matrix. So we've got Y0 is R0x as our initial guess for the solution to here. And we want to try and compute a refinement on that guess, a new rotation matrix R1, which is just that first rotation matrix with an incremental rotation applied to it. So if we assume that this R delta is small, this incremental matrix is small, then we can approximate it like this. R delta is approximately identity plus these terms here. These omegas are actually the components of the axis angle vector, if you're familiar with 3D rotation geometry. But you can just treat them as 3 unknowns. These are the Lie matrices, so we can express that R delta to a first order approximation in this linear form. And then we can do some substitution, and you end up with a linear system, and this is called linearisation. So it's making a first order approximation given an initial guess, and then solving that first order approximation to come up with a new guess, and then stepping to that location, repeating. This method is actually extremely powerful, especially when it comes to making your own custom algorithms or solving your own custom problems. As far as I know, it's used in the photosynth panoramic imaging software that aligns photographs taken in a panorama on your phone. And it's also used in the ConnectFusion 3D reconstruction algorithm. No, that's broken. Okay. ConnectFusion is the very famous algorithm that performs registration of depth images taken from different angles in real time to construct 3D models of scenes. So linearisation as a method quite often finds its way into state-of-the-art real-time algorithms. I mentioned Levenberg Marquardt before, really briefly. If you have a least squares problem, but the terms are non-linear, so here we've got a sum of squares, there's a half out the front, which is just done to make some of the maths come out more nicely. But if you have a problem of that form, which comes up quite often actually in practice, then the Levenberg Marquardt algorithm can be used. And that is an iterative algorithm where each step we solve this linear system. This J is the Jacobian, or the matrix of first order derivatives of each of those f terms with respect to each of the parameters. G is the gradient vector. And there's this parameter mu, which is varied by the Levenberg Marquardt algorithm itself. And what that mu does is it transitions the algorithm from gradient descent towards a Newton-style update. So when mu is very large, that term dominates, and that term is telling you to take a step opposite the gradient. And when mu is small, that J transpose J term dominates. J transpose J is an approximation of the Hessian matrix, or the matrix of second derivatives. And so the way the Levenberg Marquardt algorithm works is it's using a heuristic to adjust this parameter mu depending on the observed convergence. So when things are going well, it tries to make mu smaller to accelerate towards the minimum. And if convergence is not going very well, then that mu becomes bigger and it becomes more like gradient descent, which means it's guaranteed to converge to a local minimum eventually. So this is kind of a really great general purpose minimization algorithm. There are some fantastic toolboxes that have it built in. Google provide a toolbox called Ceres, and that uses automatic differentiation, which means you don't even have to compute the gradient, the first order derivatives yourself. It magically does it for you. The only constraint with this is you need it to be a genuine least squares problem. So if you just have one term, then that's not a series. You need a sum of squares, not just one number. If you've got a sum of numbers and you square root them and then square them, then that's not really a genuine least squares problem either. So if you try and fake it, it doesn't work. But if you do have a real least squares problem, then this is the default method of choice. And it's the method that's used as standard in bundle adjustment, which is a computer vision algorithm for reconstructing 3D point clouds from a set of 2D correspondences. So there's a very famous project, Building Rome in a Day, where some researchers took a whole bunch of photos just taken by the general public, and amazingly they found ways to find correspondences between them all, and then from all those photos they recovered an estimate of the pose and intrinsics of all those cameras and reconstructed a 3D model of the Colosseum. But for most bundle adjustment problems, people use a sparse version of Levenberg Marquardt to compute the solution. I'm going to just go through, well, I'm not going to go through these tools. The main limitation of Levenberg Marquardt is when you get to more than a few hundred parameters, it becomes really slow, and then you're forced to switch to different methods, which means for machine learning, where there's often hundreds or thousands or tens of thousands of unknowns, you can't use Levenberg Marquardt. You have to use normally some kind of gradient descent-based method. And then there's the general methods. BFGS is probably one of the most commonly used generic minimizers. I haven't had much success with it personally. I always try and formulate my problems into one of the other categories. This is a great book. The PDF's available online, or at least for the second edition. Some of you, I'm sure, will be familiar with it already. It has a couple of fantastic appendices that summarize a lot of things I've just talked about. It talks about algebraic solutions and Levenberg Marquardt and bundle adjustment. And if you just Google multi-view geometry, you'll find that PDF on the author's website. Okay, I've got 2 minutes, or minus 8 minutes, given that we're supposed to have 10 minutes of question time. So I'm just going to go through this last section really quickly. Overlapping roles. Oops, sorry. Where do algorithm developers sit in relation to these other positions? I don't know, we could all debate this a lot. I would say that algorithm development involves some software development and some kind of data science work, and definitely a bit of mathematics, but it is kind of a unique field that's quite different from any of those other disciplines. By the way, we're seeing a lot of applicants that would probably fall in the data scientist category, and often they are very familiar with frameworks for doing machine learning, for instance. They've used Keras or TensorFlow or scikit-learn, and they've applied it to big data problems. But often it seems that the understanding of those algorithms and those frameworks is very shallow. Gordon does most of our recruiting, so I hope I'm being fair to the most applicants here.
Yes, that's definitely what we're seeing a lot of. So if you really want to be an algorithm developer, you do need to have some idea what's going on underneath, because it's those areas that we actually make our money. Basically, what's boils down to.
That's right. So if you're using these methods, if you have them on your CV that you're an expert in linear regression or neural networks or support vector machines, it's always a good idea, I think, to have some knowledge of what's under the hood, how those methods work. To the extent, I think, if you want to call yourself an algorithm developer, that you could implement them from scratch if you had to. Of course, you might not want to be an algorithm developer after my talk, and that's fair enough too. I'm going to skip through all this stuff because we're out of time. These are the, oh, that was amazing. If you do an image search for nerd, you find all sorts of terrible pictures. If you Google for geek, it turns out that geeks are cool, and that's where I found that image. But for algorithm developers, I think you need to be a problem solver, a lateral thinker with strong math skills. And as I say, coding is very much a part of algorithm development. We do like people that when we interview them for algorithm developer roles, we expect them to be proficient in coding. Not to the extent that we would a software developer, and we do employ software developers as well. But we treat that as a very different role with very, very different requirements. But for algorithm development, we like our candidates to be able to demonstrate that they're familiar in at least one language, and it can be any language really, Python, MATLAB, C, C++, Fortran. We don't really care what the language is. We like to see that you're proficient, and maybe, like me, you misspent a certain proportion of your life learning to code. And then, as I said, also the last piece that we like to see is some domain expertise. If you're claiming certain abilities on your CV, that you can actually stand up and defend them and give convincing.
Don't put things in your CV that are not true, because I'll find out.
And yes, we are hiring. Originally, when I prepared this presentation, I assumed I'd have about 5 slides talking about how great we are as a company and why you should all come and work for us. I finished this presentation at about 3 o'clock this afternoon, so that's it. But please feel free to check out our website or email us with your CV if you think you might be interested in finding out more about ZOZO New Zealand or a career in algorithm development. I think that's it from me. I do have sorry, I said that's it, and then there's one more thing. This is what we're currently working on. So we've done ZOZOSUIT for now at least, and the next thing is fitting shoes. So we've developed the ZOZO mat. Play. I'm not sure if that would play or not. Might be broken. Okay, I think it's broken. So the idea of this one, it's a printed mat. It has fiducials on it, and you move your phone around above your foot, and we recover the camera pose from recognizing and decoding the fiducials, and then we generate a 3D model of the foot. I probably shouldn't give any details, but given there's a green screen underneath this foot, you might be able to guess how that's working. And then from that 3D model, we aim to select retail shoes that give the best possible fit. The 2 big problems with online shopping for clothes in general, including shoes, number one, that doesn't fit when it arrives, and people want to send it back, or they don't wear it, they're unhappy. Number 2 is that it doesn't look the way that the consumer expected. When they put the garment on, it just doesn't match their imagination. And so those 2 problems, we're interested in both of them, the fitting problem, but we're also interested in techniques like augmented reality, virtual reality, cloth rendering, physics engines, and so on, to tackle that visualization problem. Okay, I'm really done, sorry. Any questions?
How do you actually Well, when you started out, how did you find clients? Did you just get lucky and someone with ZOZO comes along, or is there some sort of science to finding clients?
No. In our case, we started on a couple of good leads. In fact, with NextWindow, the touchscreen company that I talked about, they actually imploded, unfortunately. That technology, optical touch, proved to be unpopular against the competition. And when NextWindow imploded, everybody at NextWindow went out into the world, in New Zealand, and new companies. And from that event, we were lucky that people knew us and they knew what we could do as the algorithm team. And we picked up a contract with Panasonic and another contract with a Taiwanese company called Pixar. And they got us going, really. In the early days, we had day jobs, and it was evening and weekends, which helps a lot, I think, not to be completely dependent on the success of your new venture.
Jamie modestly called themselves the A-team when they were in NextWindow.
That's all right. But just to briefly wrap up, we had a good start. So we launched the company on a lead. The moment I went full-time, all the work dried up for 4 months, and I had regular panic attacks. But then mostly through word of mouth and networking and just talking to people. That's how we picked up contracts until we found our big fish. Sorry.
How do you juggle the difference between being a CEO and being a algorithm developer? I guess that's where your passion is.
Yeah, that's right. Probably not very well is the answer. I probably still do more tech than I should, and more often than I should become a bottleneck for the rest of the team. So trying to learn to delegate more. When I came out of uni, I didn't like business or networking or any of that stuff at all. And I very much thought of myself as a technical person. But I guess I've fallen into it. And the business world is quite interesting as well, and the industry perspective as well. When you have your own business, you need to win clients, and you need projects of work. You can't spend a long time developing an idea and iterating on it and improving it indefinitely. You need to, make your ideas come to life quickly and find ways to make them profitable, as well as getting involved with finance and accounting and admin and governance and all the other things involved in the business. So it's a constant challenge, and I'm still trying to figure out the answer to how to be a CEO and a tech guy. And I suspect the answer is just be one or the other.
And hence we're recruiting.
Yes.
I just have a question for the 3D reconstruction of the 3D object. How many pictures have been taken for one object?
For one of the slides I showed?
Yeah, just multiple pictures for 3D reconstruction. And also, I have another question. How many cameras are in your stereoscope setup?
So for the ZOZOSUIT system, the user puts the phone down, and they stand about 1.5 meters away, and then we get them to turn through 12 positions, 30-degree increments, and that's enough to be able to reconstruct a good 3D model of the body. Are you asking in general for bundle adjustment type problems? How many images?
For example, we want to obtain the 3D reconstruction of this hand. Okay, so you have a fixed camera, or you move your stereoscope system.
Yeah.
Which one? I think that this is a fixed camera. You cannot move it.
Okay. I'm not sure if you're telling me or asking me.
I'm asking. No, I don't have any idea. I'm just asking to learn.
Yeah, okay.
So you are moving this stereoscope camera?
Not stereoscope.
A single camera.
Effectively, yes, or we're moving the subject. For our ZOZOSUIT system, the subject rotates themselves. But there's a whole ton of different methods for doing 3D reconstruction.
No, the method that you have mentioned, you change the position of the cameras or the object, as you said, with the 30-degree increments.
Yes, so that's the object is moving relative to the camera.
So is it possible to change the camera itself?
It is. Yes.
And the camera calibration that you showed with the checkerboards, it doesn't have, they will not change? Because the camera calibration is related to the, the distance between the lens of the camera, as I know.
Yes.
Okay, so time,
yes.
can we have this discussion offline? Thank you, speaker, and thank you, Jamie, for the interesting talk.
Okay, thank you. Thanks, everybody.
Thanks, and level.